Yes, thank you very much, Anna. And like my fellow panelists, I also want to thank you especially, and Konstantinos and Jens, for organizing this nice mini symposium. I also want to thank my collaborators, Yanis from Baltimore at JHU, and then Ronen and his students Or and Rotem at the Technion in Israel. We've been working on these jointly smooth functions for like a year now, and I'm actually pretty excited to share this idea with you now. I will apply them to construct effective parameters for dynamical systems, but as you maybe see later, they can also apply to many other scenarios. So why do we need effective parameters? First of all, for example, some parameters may only influence the system as a combination, and I will make all of these statements precise later. So let's say you have fuel flow and thrust in an airplane, then both together actually influence the airplane, but you cannot influence the airplane sort of independently. And also some observables or outputs of the system cannot be influenced by parameters that we control at all. So determining effective parameters that can influence certain observables is sort of the goal for this talk. And as I've said, the airplane sort of is my little example for the whole talk as well. So let's say we have fuel flow P1 as one parameter, thrust for the engine as P2 is another parameter that we can control. And then wind speed is another parameter that affects the airplane, but that we cannot control, of course. And then as observables or outputs that we can observe once we set all these parameters are, in this case, altitude and speed. And you can already see, as I've said, only a combination of fuel flow and thrust actually affects altitude and speed at the end. And also, of course, there is this unknown or at least uncontrollable wind speed parameter P3 that nonetheless affects altitude and speed. And the goal now is to determine a combination of effective parameters and also their effect on the observables that we have. So let me make this a little bit more precise. Let's say we have some parameter space of things that we can control. We have a space of observables, O, that can be observed about the system. And then let's also assume that there are some unknown parameters like the wind speed or things that we cannot control as well in the background. Let's also now say that observed values are created by an unknown function. So in this case, the dynamical system itself, just in this way. So the parameters enter, the unknown parameters enter, and then we get some observations out of it. And the only thing that we assume for our method is that we have values for the given parameters that we can control. Of course, we cannot have values for the unknown parameters, and we can also measure the observables. So for each set of parameters that we have the corresponding observations out of that function. And obviously, the simplest case that we can think about is if these unknown parameters have no effect at all, and we can just determine a surrogate model for this unknown function phi. So in this case, we can just say, okay, since we have all corresponding pairs, pi and zi, we can just fit a function phi that then, in this case, for example, approximates this one-dimensional observable z given a certain parameter p, right? So omega has no effect at all. This, of course, is a very simple setting, as you can see it here, but if you think that the parameter space is very large and the observable space is very large, then it might be still a challenge to approximate that function. So let's make it a little bit more complicated. Let's say we now have two parameters, PA and PB, and we only have one observable, Z, right? So two parameters go into one observable. And now the task would be to remove sloppy parameters. And if you want to know more about this direction, you can also search for the work by Holiday and Yanis Kefrikidis. We've done a lot of work on this problem, but this is sort of the next more complicated problem. The unknown parameters still have no effect here, but what we want to do is actually determine effective parameters, which in this case are now a function from the parameter space to some Euclidean space, such that for all parameters on the level set of these. So in this case here, the level set is sort of the same, has the same color. All observed values are the same. And as you can see here, the observed values are actually a nonlinear combination of a combination of the parameters, right? So we have PA plus PB, which can be considered an effective parameter here, and then the observables are the sign of it. But of course, a different effective parameters also satisfies this property, right? So if we choose this parameter, for example, you can see the level sets of it are the same as Z, and Z in this case even is an invertible function of this effective parameter. So the task here is sort of to reduce the whole parameter space from a high dimensional, in this case 2-dimensional space, to something that is more manageable, and that in this case only has one parameter that nevertheless still has all the power to control all observables. But as I've said before, this is still not the most challenging setting. The most challenging setting actually is this, and it's also our challenge for today. And it's special because now we have this observation noise, right? We have continuous effects of some unknown parameter omega on the observables. And the goal now is to determine this space of jointly smooth functions. That's what we invented for our method, J1 and J2 in this case, that are defined one on the parameters P, and J2, so the other corresponding jointly smooth function, is defined on the observables O, such that their values for the two pairs are exactly the same. And I will explain this in more detail with this little toy example here. So let's say we have a parameter space that is controllable by us. So we have two parameters PA and PB and samples of them in this little box. And we have this unknown parameter omega also sort of in this little cube now. And these actually cause observations, which are now in a 2-dimensional space as well. And they are just made up. So this is the function that creates this little spiral. But as you can already see, the observables here are only affected by some unknown, for now, effective parameter P effective, which is a nonlinear combination of PA and PB, and also this unknown noise. And this is what I colored here. So the unknown noise omega is sort of the arc length of the spiral. And if you look very closely, but I will also show you, the effective parameter actually is sort of the width of the spiral. And so if you're given just pairs Pi and Zi, so individual points here and corresponding observations here, then what we can test, for example, if let's say PB would be the effective parameter. And that's how it looks like. So if we just color all points by PB and essentially have PA be random, and then place the same color on the left on the corresponding points on the right, we see that certainly this is not a smooth function. So apparently, only knowing PB is not enough to know anything about the observations. Okay, so let's say, and in this case, of course, this is because PB enters as a square into the effective parameters and is smaller than 1. So PA is certainly more effective in causing these observations. So let's say we choose PA. Oh, okay. Now the function looks like this, right? Because only PA varies. And if we then color the corresponding points, you can already see that now the width of the spiral actually starts to appear, right? And this is because PA has a much stronger effect on the observations here than PB. But it's still not a smooth function, right? There's still some noise here. And if we actually choose the correct effective parameter that was used, we can see here that it looks like this quadratic function, and on the right, it's a perfectly smooth function. So ideally, we can identify these functions automatically just from these known pairs Pi and Zi. We do not need to know anything about this actual effective parameters, and we don't know anything about the noise, right? We only have Pi's and Zi's. This is the goal of the algorithm. So the requirements for these jointly smooth functions are that we have these two data sets, P and O in this case, and we have corresponding pairs Pi and Zi. And then we want all jointly smooth functions to satisfy that they have the same value so that we can have this nice corresponding picture. And they should also be smooth, right? But of course, what does it even mean for two functions to be smooth on a data set? And also, what does it mean to be for one function to be smoother than the other function, right? We cannot just choose the space of all smooth functions like C infinity or C2, because these functions can look like this, for example, and they're still differentiable in the sense. But what we actually want to quantify is that these functions are smoother than the other functions on the right. And of course, this is not a new idea. We can actually use the Dirichlet energy of arbitrary functions to measure how oscillatory they are. And for our work and our method, we will actually use the Dirichlet energy of kernel eigenfunctions on the two individual sets, because they can even be ordered in this way. And if you know anything about squared exponential kernel eigenfunctions, for example, you will immediately recognize that these are kernel eigenfunctions, at least on a circle. And so the main idea will be to select functions that have a small component in the higher eigenfunctions. And this is what is defined on this slide here now. So what we do actually is sort of define an inverse Dirichlet energy that is not larger if the function is more oscillatory, but it's actually larger if the function is less oscillatory. Because, let me quickly go through this first definition here. For a certain number of eigenfunctions that we want to pick in a given function, which now on a data set of finitely many points n is just a vector, right? Because if we evaluate a real valued function on a data set of n points, then it becomes a vector. We define this detruncated energy with respect to a kernel, kx, by this, right? And this is looks maybe a little bit strange, but it only is the projection of the vector onto the first d eigenfunction of the kernel. So what we take is essentially a few of these low oscillating functions, like the constant function, the sine function, and so on, and then project the function on it. And once we do this, we can say that a function that has norm 1 on the data and also has energy 1. So this squared norm here is equal to 1 with respect to this kernel, then we can call it smooth. Because if you think about it, if the function has norm 1 and also the projection onto the first d eigenfunction is 1, then it means the function is just a linear combination of those very smooth and nice eigenfunctions. So if both of these things are true for a given function, then A, we call it smooth, and B, it's a linear combination of the first few eigenfunctions. And of course, now we can define jointly smooth as well, because now if we take two data sets, X and Y, or the parameters and the observations, and construct two kernels, and then see if a given function is actually having norm 1 and a truncated energy equal to 1, we call it jointly smooth. These definitions might seem a little weird, but it's very easy to see why we did this using this algorithm here. And that's actually the algorithm that is sort of the main focus of the talk, because you can easily implement it and it will construct these jointly smooth functions. It actually will even create a whole space or subspace of jointly smooth functions. So let's briefly go over it. We have given two sets, so parameters and observations, Y, for example. And we have pairs of these, right? This is really important. And the output of the algorithm then is a selection of capital M jointly smooth functions. And the way it works is that we separately construct two kernel matrices, Kx and Ky, on the parameters X and the observations Y. We then compute individually the first d eigenvectors, where the number d can be relatively large, so let's say between 100 and 1,000 eigenfunctions or eigenvectors in this case of these matrices. And then comes the sort of weird step because we concatenate these eigenvectors into one large matrix now, which has 2D columns, and then construct the SVD of that, where the jointly smooth functions are now the mth column of the matrix U. And the reason this works is that since eigenvectors of matrix Kx are smooth on the one data set, and eigenvectors of the matrix Ky are smooth on the other data set, if we concatenate them and then again construct a basis for that function space using the SVD, we essentially get a sorting of all the functions that are smooth on both. And actually the singular values here, and I will not show this, but we have a proof in the paper, the singular values sort of sort all the functions by their smoothness on both data sets. So it's a really nice theoretical result as well. And if we actually apply this algorithm now to our toy example first, so with input Pi and Zi for all these points, you can see that there's a nice increasingly oscillatory set of smooth functions here that are both smooth on the parameter space here and also on the observation space down here. And if you compare it with the actual effective parameter of the system that is shown here, you can see that neither of these smooth functions actually is the given effective parameter, but we are not really searching for that either. We are actually just searching for a whole space where then in principle that effective parameter here is a linear combination of those functions. And if we then go to our little airplane example again, and now formulate it as a dynamical system where I must say I'm a mathematician, so I'm not really fond of very large, complicated examples. So this is a very simple example. It's actually just a linear pendulum parameterized by these three parameters. So thrust, fuel flow P2, and then the unknown wind speed P3. And then we made it a little nonlinear. So you can see the trajectories of our airplane as it approaches a certain target speed and target altitude just are nonlinear distorted from the regular damped pendulum equations. And if you change the parameters, this steady state will change and also the trajectories will change. But there's always a stable steady state at this particular value here. And what we are asking now is we have knowledge of P1 and P2, right? Because these are the parameters we can control. And we want to see how they affect the final steady state of the airplane. So the final speed and the final altitude of that airplane. And if we do this, like if we sample a lot of parameters in this box, and for each parameter, we get a final state x1 and x2, right? That then corresponds to one of those steady states. And then color this parameter space by our known effective parameter in this case, you can see that it has this shape. And of course, once we actually apply the jointly smooth function algorithm, we will see that we get a lot of these smooth functions. And as you can see, the color in the back is this jointly smooth function, and the level sets are the true known effective parameter. And you can see they follow that very nicely. And if we plot our true effective parameter against these jointly smooth functions, phi1, psi2, and psi3, you can see that it actually is a nice and smooth functions, at least on that data. So in this case, we could identify both a nonlinear combination in parameter space that then will affect a nonlinear combination of, in this case, the final speed and altitude of the airplane. But this algorithm, as I said at the beginning, cannot just be applied to dynamical systems and parameters and so on. What we did in the paper was also applied to sleep data, for example. And what I also haven't shown you is that we can apply it to multiple sets of data, not just two. So we can actually find jointly smooth functions for a lot of different data sets as in one go, so to speak. The thing we did here was there was a large data set of EEG data, so from sensors on the people's brain that was recording them during the night. And then an expert was labeling the sleep REM and S1 and S2 sleep data. So each trajectory, so to speak, had a label by an expert. And what we did then was take individual data sets of these trajectories measured from one subject. And for each of the data sets, we considered them as one separate data set and then constructed jointly smooth functions for all the different sleep stages. And since we know the labels from the expert, we can also train a classifier on this new feature space that we get from the jointly smooth functions and compare it to other methodologies that can do similar things like our jointly smooth functions. For example, the kernel CCA, or if you know the nonlinear CCA, and general linear CCA is also possible. And in this case, if we use kernel CCA, which I guess is the closest approach to the jointly smooth function approach, we get a classifier accuracy of 85%. And with the jointly smooth functions, we get a classification accuracy of 98%, so which essentially means that the first 20 jointly smooth functions of these 6 sleep stages trajectories capture a lot of the different variability of the sleep stages, while the kernel CCA sort of mixes them up, and then the classifier cannot really learn what sleep stage is actually currently present. I'm almost at the end of my talk. The take-home message is that jointly smooth functions can help identify effective parameters, of course. And there's a lot of things I didn't discuss that you can read up in the paper. For example, that we can also extend the functions to new data points as they come in. We can also detect which of these smooth functions are actually smooth and which are just noise, which is a nice theoretical result as well. As I said, we can also apply it to more than 2 data sets and also compare it to nonlinear CCA and alternating diffusion maps if you know about this. What we haven't done yet is identify effective parameters in very large systems, like with tens of thousands of parameters, for example, study the computational efficiency of the method. And what I would also like to do is use these for model predictive control at the end. So thank you very much for listening. And I hope you have a better idea of what jointly smooth functions are now. And please take a look at our paper. If you have questions after the conference, you can just contact me by email. Thank you.
Thank you very much, Felix, for your excellent talk. I think we still have time for 1 or 2 questions. Are there any questions from the audience? I don't see any questions popping up in the Q&A so far. Yes, I think, yeah, Jens, you want to say something?
Yeah, sorry, I popped in later because of some administration nonsense I had to do. My question would be, do you have any ideas how to deal with these very large systems? What type of extra approach is required for this?
So this is, I guess, the third last point here. Thanks for the question. Yes. So if we have very large systems with a lot of parameters, tens of thousands of parameters, and also tens of thousands of observations, for example, then the key problem is to construct the kernel matrix, right? Because it could be the case that we are lucky and that only the ambient space of the system parameters is large. So for example, if we just sample a line in a 10,000 dimensional parameter space, then there's no problem because we can easily use kernel methods for that. And of course, the corresponding observations will then also be a line. But if the space, the sample space is really 10,000 dimensional, then I would also ask you how to actually sample such a large space. But also the key problem then is to construct the kernel, because once we have the kernel matrix ready, then it's independent of the dimension of the space. Right, so then I guess the key problem is to select the correct kernel, or if you want to select the correct metric between two different points in either parameter or observation space.
And do you have an idea how to approach this? Or?
Well, you can either look at different kernels, like there's a whole range of different kernels, and there's also this nice analogy between neural networks and kernels. Like, for example, you can use a convolutional neural network, turn it into a convolutional kernel that corresponds to that convolutional network, and then directly use that kernel for images, for example, which also are extrinsically high dimensional. Another possibility would be to first reduce the parameter space in dimension, like, for example, apply PCA and then construct the kernel on the first 5 principal components. And yet another approach would be to use hyperparameter optimization for a given kernel class, right? For example, you can say we have a kernel that has a certain bandwidth or a range of bandwidth for each dimension. And then we first search for a good bandwidth for each dimension, and then use that kernel for jointly smooth functions.
Thanks a lot, yeah.
Sure.
During your answer, there popped up one more question by Dmitry Todorov. What would be the worst enemy of this approach?
The worst enemy of this approach probably is if there's no effective parameter in the system at all, right? So if the parameters don't affect the observations at all, and all observations are just caused by noise, right? Because then you cannot find any smooth function except for the constant function, of course. And then the approach must fail, because you cannot construct a full space of nice functions with just a constant function. Of course, another worst enemy, if you want, is the second point from below here. Because if you've worked with kernel methods, you probably know that they don't scale well if you use a brute force approach, right? If you constructed let's say a pairwise distance matrix for the exponential kernel with 1,000,000 points, then you have 1,000,000 by 1,000,000 matrix, which is 10 to the 6 squared entries in the matrix. And of course, you don't really want to store that amount of data. So you certainly have to put in some work to get a large amount of data points working with this kernel approach. Thanks for the question, though.